So in the first part of this chapter, you learn the nature of light. That light is both a particle and a wave. We know that light is a wave because it has the characteristics of a wave. It has frequency, wavelength, and amplitude. And we also know that light is a particle. Einstein was able to prove this using his photoelectric effect, that light basically contains massless consists of photons, which are massless particles of light. And the physicists at the time, they were able to prove the relationship between energy and frequency, as well as wavelength. So you can convert a frequency of light or a wavelength of light into energy using two equations that you learned in the first part. Either E equals h nu, where h is Planck's constant, or E is equivalent to hc over lambda, where h is Planck's constant, c is the speed of light, and lambda is the wavelength of light. So based on those equations, the longer the wavelength of light, the lower the energy and frequency, and vice versa. And so the shorter the wavelength, the higher the energy and frequency of that light. And finally, you also learn that atoms of any element have the ability to absorb energy as well as emit energy in the form of light. So when an atom absorbs energy, the electron inside the atom absorbs that energy and goes to a higher energy level. So it makes a transition from the ground state, which is the lowest energy level, to the excited state, which is a higher energy level. And because this electron at the excited state is unstable, it has to go back down to a lower energy level. And when it does, it has to release or emit energy in the form of light. The hydrogen atom, for example, can emit different wavelengths of light with different energies. And Niels Bohr was able to quantify the amount of energy that's released by the hydrogen atom. And so he proposed this model of the atom, and he was awarded the Nobel Prize for this discovery. And that's basically the last thing that you learned in the first part of this chapter, which is the Bohr model of the atom. So Bohr proposed that an atom consists of a nucleus at the center containing protons and neutrons, and then you have these orbits or stationary states, as he called them, where electrons orbit the nucleus, just like the planetary model. The Bohr model of the atom, however, is incomplete, and it only works for a hydrogen atom or any system containing one single electron. And it doesn't work for a multi-electron system. In other words, it doesn't work for larger atoms like helium, lithium, beryllium, and the other heavier elements. The quantum mechanical model of the atom is a more complete model compared to the Bohr's model of the atom. The quantum mechanical model can explain the behavior of electrons, how they exist in atoms, and how they determine physical and chemical properties. And this is the main topic of the second part of this chapter. So in the first part of this chapter, you learn that light is a wave, and we know it's a wave because it has frequency, wavelength, and amplitude. One other characteristic that a wave has is that they can interact by interference. Waves interact by interference, and there are two different types of interferences. The first one is constructive interference. What that means is that if you have two waves that are in phase, meaning they line up with the same wavelength or similar wavelength, then they will interfere with each other constructively. So what that means is they add up and turn into a larger wave with a larger amplitude, right? This is height right here. So this is a larger amplitude. The other type of interference is called constructive interference. So what that means is that if you have two waves that are out of phase, then they cancel each other out. And so they interfere destructively. So what you see is basically nothing. Absence of light, because they interfere destructively. They cancel each other out. And because of this, waves exhibit what they call diffraction patterns. And diffraction patterns are basically interference patterns resulting from the bending or diffracting of waves when they encounter an obstacle of comparable size to its wavelength. So essentially, if you have a wavelength of light, let's say a red laser, okay, and a red laser typically has a 700 nanometer wavelength. And so if you have a nanoparticle that's about the same size as the wavelength of light, 700 nanometers, then that light will interact with that obstacle, with that object, causing what they call diffraction pattern. So to explain this phenomenon, there's this one famous experiment they call double slit experiment, where you have a light source, and this light basically passes through a wall with a slit, a hole, and then there's another barrier here, another wall with two slits, a double slit, and then a back wall at the very back, right? So if light is acting as a wave, then it will pass through that hole as a wave, and then passes the other two holes also as a wave instead of as a particle. And so because these waves are interacting with each other, they will cause interference patterns. Okay, so you have this dark spots and white, you have dark spots and bright spots, which are basically the results of interference. So if you have dark spots, that means you have a destructive interference. And if you have bright spots, then those are constructive. Those are the results of a constructive interference. And this is what they call a diffraction right here. This is the diffraction pattern. So light and electrons actually have a lot of things in common in such a way that electrons also have both wave-like properties and particle-like properties. So if you remember, the electron was discovered in the early 1900s by J.J. Thomson. And they already know that an electron is a particle. It's a subatomic particle within an atom. But they didn't know that it actually also has wave-like properties. So it was Louis de Broglie who proposed the wave nature of the electron. So Louis de Broglie was able to prove this using this slight modified double slit experiment. So instead of using a beam of light, he used a beam of electrons. And this double slit experiment shows that the wave nature of the electron is an inherent property of individual electrons. He was able to prove this because of the fact that these electrons were able to produce an interference pattern similar to a light wave. So because the electrons have wave-like properties, the electrons were able to produce an interference pattern. And de Broglie basically proved that experimentally. And he was also able to prove this mathematically. So he used this mathematical equation shown here to prove that an electron has a wavelength. So basically anything that has wave-like characteristics should have a wavelength, frequency, and amplitude, and so on. And so he proved it using this equation shown here. So this is the wavelength of an electron is equivalent to Planck's constant divided by the mass of an electron times its velocity. So the de Broglie relation basically relates wavelength, velocity, and energy of the electron, because lambda, the wavelength, is related to energy and frequency. So the faster the electron, right, because the velocity is being divided here in the denominator, the higher the value of the velocity, the smaller the wavelength. Let me say that again. The faster the electron, the higher the kinetic energy of the electron, and so the shorter the wavelength of that electron. Because the mass basically remains constant. And the mass of an electron is equivalent to 9.11 times 10 to the negative 31 kilograms. So let's look at an example here. Calculate the wavelength of an electron traveling with a speed of 2.65 times 10 to the 6th power meters per second. So we know the equation for wavelength, the Broglie relation, right? The wavelength. And that's equivalent to Planck's constant divided by the mass of the electron times its velocity. We know the mass of the electron, we know the velocity, we also know Planck's constant. And so all you have to do now is plug in the values into this equation. And so when you do that, we get a value equivalent to 2.74 times 10 to the negative 10 meter, which is basically less than 1 nanometer. So that's the wavelength of an electron. So with regards to the velocity of an electron, according to Heisenberg's uncertainty principle, the more accurately we know the velocity of an electron, the less accurately we know its position, and vice versa. And the experiment that de Broglie did to prove that an electron is a wave, it's called the single electron diffraction experiment, basically demonstrates that we can't observe the wave nature and the particle nature of an electron at the same time. And he proved that mathematically using this equation shown here. So you can see that delta x times mass of the electron times delta v is greater than or equal to h divided by 4 pi, where h is Planck's constant, delta v is the uncertainty in the velocity, delta x is the uncertainty in the position. So based on this equation, delta x is inversely proportional to delta v. So what that means is that as the uncertainty in the position increases, delta v decreases. So when we say that the more accurately we know the velocity, then the delta v would be a lower value, right? So when delta v is lower in value, then delta x, the uncertainty, would be extremely high. So that's what it means by Heisenberg's uncertainty principle. The more you know the position, the less you know about the velocity, and vice versa. And this is basically when Heisenberg introduced the idea of what they call complementarity, which means that an electron is observed as either a particle or a wave, but never both at the same time. So if you want to test whether an electron is behaving like a wave, then you won't be able to determine that it's behaving as an electron or as a particle at the same time. Or if you want to test whether an electron is behaving like a particle, then you won't be able to see the wave-like characteristics of the electron. And this is different from Newton's laws of motion, which is basically classical physics. And Newton's laws of motion are deterministic, which means that you can predict by just looking at an experiment, right? So let's say that you have two baseballs. Two baseballs were hit at the same time with same velocities, same position, same angle, and so on and so forth. Those two baseballs will land in the same spot every single time. So that's what it means by deterministic. So according to classical physics, when you hit a baseball with the specific force, specific angle, disregarding air friction and all that stuff, that baseball will always land in the same spot. Okay, so you hit a second baseball, it'll have the same trajectory as the first one. And you do it again the third time, fourth time, fifth time, it's always the same. So that's basically what classical physics is. But when it comes to electrons, so let's say you give an electron a specific force, you hit it, specific angle, it will never have the same trajectory. It's always different. And it may land in the same spot, but it's not exactly the same spot every single time. So this is what they call a quantum mechanical probability distribution map. So when you hit an electron, it could have this trajectory up here. When you do the same thing for a second electron, it might have this trajectory down here, and so on and so forth. So this is what they call a probability distribution map. It's statistics. It's based on statistics. So in other words, we can't know an electron's trajectory. It's indeterminate. An electron's behavior can only be described statistically. And that's why quantum mechanics or quantum physics is also known as statistical mechanics, because it's all about probability. It's all about statistics. So although we don't exactly know where the electrons are, we have an idea of where they are likely to be found. So electrons are more likely to be found inside the orbitals. And orbitals, by definition, are probability distribution maps where electrons are likely to be found. So in quantum mechanics, these electron orbitals are described by what they call quantum numbers. And there are 4 different types. The first one is called principal quantum number, and it has the symbol lowercase n. The second type is called angular momentum, and it has the symbol lowercase l. And this is also known as the azimuthal quantum number. The third type is called magnetic quantum number, and it has a symbol m sub l. So the L is the subscript. And the last type of quantum number is called the spin quantum number, m sub s, where s basically stands for spin quantum number. And all of these quantum numbers have specific numerical values. And we'll talk about them, every single one of them, in greater detail. So let's look at these quantum numbers in a little bit more detail. So the first one again is called principal quantum number, and it has the symbol lowercase n. And what this tells us is the size and energy of the orbitals. And by definition, orbitals are the regions of space where electrons are likely to be found. So there's a high probability of finding an electron in these orbitals. And these principal quantum numbers have numerical values. So they are whole numbers only. And the lowest value is equal to 1. So it starts at n equals 1. You can have n equals 2, 3, 4, so on and so forth. Whole numbers only. You can't have fractions. You can't have 1.5 or 2.5, 3/4 or any fraction. So it's always a whole number. You can think of this principal quantum number as the stationary states. So if you can visualize Bohr's model of the atom, where you have orbit number 1, orbit number 2, 3, and 4, you can think of those as principal quantum number. So you have principal quantum number 1, principal quantum number 2, and so on and so forth. And this principal quantum number basically represents the energy level, and that's why principal quantum number n is also known as the main energy level. And now you can call those stationary states main energy levels. So you can have energy level 1, energy level 2 for n equals 2, energy level 3, so on and so forth. And these energy levels, of course, have specific energy, and you can calculate the energy of that energy level using this equation shown here. So E sub n is the energy at a specific energy level, is equivalent to negative 2.18 times 10 to the negative 18 joules times 1 over n squared, where n, of course, is the main energy level, or the principal quantum number. So if you have n equals 1, then you have E1, E sub 1, is equivalent to negative 2.18 times 10 to the negative 18 joules. So that would be the energy of whatever that electron at that specific energy level, n equals 1. However, this equation actually only works for the hydrogen atom. Again, this is based off of the Bohr model of the atom, right? So as I mentioned earlier, Bohr's model of the atom is actually not complete. It only works for single electron system, like a hydrogen atom. So it doesn't work for multi-electron system like larger atoms like helium or lithium, beryllium, or heavier elements. And this numerical value right here, negative 2.18 times 10 to the negative 18 joules, is actually known as the Rydberg's constant. Again, this only works for a hydrogen atom. So the higher the energy level, in other words, the higher the n value, the higher the energy of that orbital or electron. For example, if you have electrons in n equals 3 versus electrons in n equals 1, then those electrons in n equals 3, or the third energy level, would have higher energy than the electrons in the first energy level. So the second type of quantum number is known as angular momentum, and it has the symbol lowercase l. So what this tells us is the shape of the orbitals. And just like the principal quantum number, the angular momentum quantum number has specific numerical values. And the values of L are actually dependent upon the value of n, the principal quantum number. And so the possible values of L are from 0 all the way to n minus 1. Okay, so it's a range basically, right? And the minimum value of L is 0. So the lowest possible value of L is 0 up to n minus 1. So for a given value of n, L can be any integer, including 0, up to n minus 1. So for example, if we have n equals 3, right? Third energy level, n equals 3. The possible values of L are 0 all the way to n minus 1. So 3 minus 1 would be 2. So the possible values of L are 0, 1, and 2. So there are 3 possible values of L for n equals 3. Each value of L has a letter assigned to it. So if you have L equals 0, the letter assigned to it is S. When you have L equals 1, that's P. If you have L equals 2, that's D. L equals 3 is F. So you can think of angular momentum like an energy sublevel. Okay, so it's a level within another level, right? So an energy sublevel. So these are called energy sublevels. And we can talk about sublevels in a little bit more detail later. So within these energy sublevels, what you have are orbitals. And within the orbitals, you have electrons inside them. So make sure that you remember what these L values represent. Okay, so again, L equals 0 represents the S sublevel. L equals 1 represents the P sublevel. L equals 2, the D. L equals 3, the F, and so on and so forth. After F, it's basically the next letter in the alphabet, G, right? So if you have L equals 4, that represents G sublevel. If you have L equals 5, then that would be H, and so on and so forth. So the third type of quantum number is known as the magnetic quantum number, and it has the symbol M sub L. And what this tells us is the orientation of the orbital, in space. And just like the first two quantum numbers, the magnetic quantum number also has numerical values. And the numerical values for M sub L are actually dependent upon the angular quantum number, L. And so the values of M sub L are from negative L to positive L, including 0. So let's look at some examples. If you have L equals 0, then the only possible value of M sub L would be 0, because it's from negative L to positive L, including 0. But you can't have negative 0, obviously. If you have L equals 1, then it would be the possible values of M sub L would be from negative 1 all the way to positive 1, including 0. So you have 3 possible values of M sub L when L equals 1. Okay? And if you have L equals 2, then it would be negative 2 all the way to positive 2, including 0. So that would be negative 2, negative 1, 0, positive 1, and positive 2. So a total of 5 different orientations of the orbitals. And if you have L equals 3, that would be from -3 to +3, including 0. And the last type of quantum number is called the spin quantum number. And it has the symbol m sub s. And what this tells us is the orientation of the electron's spin within a given orbital. And this also has a specific numerical value. The orientation of the spin is quantized with only 2 possible values. So quantized means that there's only specific discrete values allowed for this quantum number. And so those 2 possible values are either positive half or negative half. So those are the only possible 2 possible values for m sub s, magnetic spin quantum number. And so if you have an electron that's spinning up, it's given a positive half value. And if it's spinning down, then that electron is given a negative half value. So orbitals with the same value of n, the principal quantum number, are said to be in the same principal energy level. And so again, if you visualize Bohr's model of the atom, you have the nucleus at the center, and then you have the stationary states or orbits surrounding the nucleus. And again, these are now called principal energy levels. So you have n equals 1, the first principal energy level, n equals 2, the second energy level, n equals 3, 4, 5, and 6, and so on. So each circle is a principal level or principal shell, or you can just call it energy level. And n equals 1 again is first energy level. Orbitals with same value of n and L are said to be in the same energy sublevel or subshell. And so, for example, the 2p sublevel are in the same energy level because they have the value n equals 2, right? So you have this coefficient here is basically the energy level. So both the 2p and the 2s sublevels are in the same principal energy level. The 2p sublevel contains p orbitals, and the 2s sublevel contains only the s orbital. So the p orbitals in the 2p sublevel are all in the same sublevel. So those orbitals have the same value of n and L. Same thing with the 3p sublevel. So the 3p sublevel contains p orbitals, and there are 3 of them, 3 p orbitals. All those orbitals in the 3p sublevel have the same value of n and L. So let's take a look at an example here. So we have the energy levels, n equals 1, 2, and 3. And based on these n values, you have specific L values, right? Remember that L value, the values of L are dependent upon the value of n, from 0 all the way to n minus 1. And so if you have n equals 3, then you have 3 possible values of L, from 0 all the way to n minus 1, which is 3 minus 1 is 2. So from 0 all the way to 2, 0, 1, and 2, those are 3 different values of L, and they have specific letters assigned to them, right? S, P, D, and F. So if you have L equals 0, then that's a 3S or S sublevel. If you have L equals 1, that's P. L equals 2, that's D. So you have these sublevels, 3D, 3P, and 3S. And we can do the same thing for n equals 2 and n equals 1. What are the sublevels based on the n value? All right, so for n equals 2, you have L values of 0 and 1. And so you have 2s and 2p. Those are the only possible sublevels within that energy level. So we have the 2s and the 2p. And for n equals 1, the only value of L is 0 because it's n minus 1. So 1 minus 1 is 0. So the only value of L is 0, and 0 represents S. And so we only have one S sublevel. How many orbitals exist in each energy sublevel? Well, that will depend on the value of m sub L, right? The magnetic quantum number. So for 3D, for example, the L value is 2, right? For L equals 2, you have the D sublevel. And if L equals 2, then the possible values of M sub L are -2 all the way to +2, including 0. So that would be -2, -1, 0, 1, and 2. So that means that you have a total of 5 orbitals. So each M sub L values basically represents the orbital. So you have a total of 5 different orbitals. For a P sublevel, you would have L equals 1. And the possible values of ML are -1, 0, and 1. 3 different values, which means that there are 3 orbitals in the 3p sublevel. And you can do the same thing for S, P, and D, and F, right? So for 3s, there's only one value because S is L equals 0, and so M sub L would be 0. So you only have one orbital in an S sublevel, or any S sublevel. So that means 2s is the same thing. You only have one orbital there. For 2p, a p sublevel contains 3 orbitals. And the 1s at the bottom, 1 orbital. All right, so now let's take a look at a few things here. So this is basically what we did in the previous slide. You were able to determine the sublevels based on the value of n, and you were able to determine the number of orbitals based on the values of m sub L. So there's a shortcut in determining the total number of sublevels per given energy level. So here you notice that when n equals 1 on the first energy level, you only have one sublevel available. When n equals 2, there are 2 sublevels available. When n equals 3, 3 sublevels available. So now you kind of see the trend here. The number of sublevels per energy level is basically equivalent to the energy level, the principal level. So you can predict that n equals 4 would have 4 sublevels. So here the maximum number of sublevels per energy level is equal to the value of n. Okay, so if you have, again, n equals 3, then you have 3 sublevels. If you have n equals 4, you have 4 maximum sublevels. N equals 5 would be 5 sublevels. On the right-hand side here, we have number of orbitals. There's also another way to determine the maximum number of orbitals possible per given sublevel. So how can we determine the number of orbitals per given sublevel? There's an equation for it. The maximum number of orbitals per sublevel will depend on the value of L. And we can determine that by using this formula 2L plus 1, where L is the angular momentum, or the value of L. And so if you have L equals 0, plug that into the equation 2L plus 1. 2 times 0 is 0, plus 1 equals 1. That means that for L equals 0, the maximum number of orbitals that can fit inside that sublevel is 1, only 1. For L equals 1, 2 times 1, using this equation, 2 times 1 is 2, plus 1 is 3. So that means that for L equals 1, a p sublevel can contain a maximum of 3 orbitals. For L equals 2, which is the d sublevel, can occupy a total of 5 different orbitals. And L equals 3, which is the f sublevel, can have a total of 7 orbitals. So if you have L equals 4, the maximum number of orbitals would be 9, right? So it's basically 1, 3, 5, 7, 9, 11, and so on. So that's basically the trend in determining the maximum number of orbitals given the value of L. Or you can use that equation 2L plus 1. What about maximum number of orbitals per energy level? So if I ask you how many orbitals can exist maximum in the first energy level. Okay, so there's a shortcut to that. All you have to do is use n squared for the maximum number of orbitals per energy level. So in energy level 1, for example, the maximum number of orbitals is 1. Because 1 times 1, or 1 squared equals 1. For n equals 2, that would be 2 times 2 is 4. So you have 4 orbitals. What are those orbitals? Well, you have the 2 coming from the 2s and the 2p, right? So in the 2s, you have 1 orbital. In the 2p, you have 3 orbitals for a total of 4. 3 plus 1. For n equals 3, 3 times 3 is 9. 9 orbitals that can exist coming from the 3s, 3p, and the 3d. So add 5, 3, and 1, and you get a total of 9 orbitals in that third energy level. For n equals 4, that would be a total of 16, n equals 5, 25 orbitals, and so on. And last but not least, we can also determine the maximum number of electrons that a single orbital that can occupy. Every orbital, okay, any orbital can only hold a maximum of 2 electrons. So if you have an s orbital, that can hold a maximum of 2 electrons. A p orbital, a d orbital, or an f orbital can hold a maximum of 2 electrons. Okay, but if we're talking about sublevels, like for example, if we have an s sublevel, still maximum of 2 electrons. A p sublevel contains 3 different p orbitals, and if you have 3 p orbitals and each orbital can hold a maximum of 2, then a p sublevel can hold the maximum of 6 electrons. Same thing with the d and the f, right? So if you have a d sublevel, that contains 5 different orbitals. You multiply that 5 orbitals by 2 electrons, and you get a maximum of 10 electrons in the d sublevel. Same thing for the f sublevel. You have 7 orbitals, multiply that by 2 electrons, 14 electrons in the f sublevel. But always remember that for any orbital, the maximum number of electrons that they can hold is 2 electrons. All right, so let's take a look at this example shown here. What are the quantum numbers and names, example 2s and 2p, of the orbitals in the n equals 4 principal energy level? How many n equals 4 orbitals exist? So the quantum numbers we're going to take a look at are the principal energy level, or principal quantum number, the magnetic quantum number, and the angular momentum. And so we're being asked for the quantum numbers and names. So we'll look at the values of n, the values of L, and the values of m sub L. And we don't have to worry about m sub s, the electron spin quantum number, because we know that it's always positive half or negative half. So we have n equals 4, right? We're given n equals 4. So the values of L will depend on the value of n, right? So L is equivalent to 0 all the way to n minus 1. So that means from 0 all the way to 3, because n equals 4 minus 1 is 3. So the possible values of L are 0, 1, and 2. 0, 1, 2, and 3. All right, and so the values of m sub L, the magnetic quantum number, will depend on the value of L. So if you have L equals 0, the only possible value of m sub L would be 0, because it's from negative L to positive L, including 0. When L equals 0, mL would be negative 1, 0, and positive 1. For L equals 2, you have negative 2, negative 1, 0, positive 1, and positive 2. And the last one would be from negative 3 all the way to positive 3, including 0. So these are the values of the quantum numbers. What about the names? What about the names of the orbitals? So if you have L equals 0, then that represents the s orbital, okay, or the s sublevel. And so for the first one, that means we have the 4s, and there's only one orbital there. The second one, for L equals 1, the sublevel is P, right? So you have a 4P, so you have a 4P, 4D, and a 4F. So the names of the orbitals are 4s, 4p, 4d, and 4f. So there's a total of 7 orbitals in the 4f sublevel. You have 5 orbitals in the 4d, 3 orbitals in the 4p, and 1 orbital in the 4s. So at the beginning of this chapter, you learn about orbitals. And according to the quantum mechanical model, electron orbitals are defined as high probability distribution maps where electrons are likely to be found. So in other words, orbitals are regions of space where there's a high probability of finding an electron. So outside the orbitals, you will not find an electron. There's 0 probability of finding an electron outside the orbitals. There are several different types of orbitals. There's the s orbital, the p orbitals, d orbitals, and f orbitals. So you can only have one type of s orbital. There are 3 different orientations of the p orbitals. There are 5 orientations of the d orbitals and 7 for the f orbitals. And each orbital, if you remember, can only hold a maximum of 2 electrons. Okay, so a sublevel is different from an orbital. So if you have an s sublevel, you have an s orbital. If you have a p sublevel, you have 3 different p orbitals. A d sublevel has 5 different d orbitals, and an f sublevel has 7 different f orbitals. And so now we're going to take a look at the different shapes of these orbitals, from s all the way to f orbitals. So again, orbitals by definition are regions of space with high probability of finding an electron. The shape of the orbitals is determined by the value of L, which is one of the quantum numbers, right? It's the angular momentum quantum number. And so if you have L equals 0, that tells you that you have an s orbital. If you have L equals 1, that indicates that you have p orbitals, L equals 2, d orbitals, and L equals 3 would be f orbitals. So let's take a look at this first one here, the s orbital. What does an s orbital look like? According to the quantum mechanical model, an s orbital is basically a sphere, right? So if you have an xyz coordinate, right, a 3-dimensional graph, what you're looking at for an s orbital is a sphere. Okay, so it's spherical in shape. And so, for example, if you have a 1s orbital, you have an s orbital in the first energy level, principal energy level 1, right? N equals 1. And because you have a 1s, you have n equals 1. And because you have an s orbital, that means the sublevel or the orbital is in the L equals 0. And that makes sense because the value of L is dependent upon the value of n, right? L is equivalent to 0 all the way to n minus 1. And if you have 1 for n, 1 minus 1 is 0. So the only possible value for L in this case is 0. You can also have a 2s orbital, an s orbital in the second energy level, okay, within the second energy sublevel. So here we have n equals 2, and the L value here can be from 0 all the way to n minus 1. So that means that if you have L equals 0, L equals 1 is also possible. But because we have specifically an s orbital or an orbital in the s sublevel, the value of L must be 0 because s corresponds to L equals 0. If L equals 1, then that means we have a p sublevel. And inside the p sublevel, you have the p orbitals. But because we have a 2s, the value of n is 2, and the value of L is 0. And when it comes to energy, the 2s orbital is higher in energy than the 1s, right? Remember that the principal quantum number tells you about the size and the energy of these orbitals. And so because we have n equals 2, the 2s orbital is higher in energy and larger than the 1s orbital. Same thing for a 3s orbital. So if we're comparing a 3s orbital versus a 2s orbital, the 3s would be higher in energy and larger than a 2s orbital. And you can predict a 4s and a 5s and so on and so forth. The higher the principal energy level, the higher the energy and the larger the size of that orbital. And so that's basically how you can compare energy and size for a specific orbital. And it's also true for the other orbitals like the p orbitals, the d orbitals, and the f orbitals. So now if you cut a small cross section of these orbitals, this is what they would look like inside. Right? So if you have a 2s orbital, you have these shaded regions and unshaded regions. And the shaded regions are where the electrons can be found. Whereas the unshaded region, those are what they call nodes. And the nodes, inside or in the nodes, electrons don't exist. Okay, because they don't have the proper energy to exist there. Okay, remember that these quantum numbers are quantized, meaning they have a specific discrete energy. And so in these nodes, electrons cannot exist. So there's zero probability of finding an electron in the nodes. All right, so now let's move on to the p orbitals. Remember that the p orbitals exist in the p sublevel. And in the p sublevel, the value of L, the angular momentum quantum number, is 1. So L equals 1. And the shape of the p orbitals is dumbbell in shape. Okay, and there are 3 different p orbitals. You have 3 different orientations of the orbitals. You have the p sub x, p sub y, and p sub z. So the x, y, and z, these are subscripts. Okay, telling you how the orbitals are oriented in space. So let's take a look at what an orbital looks like. So again, we have 3 different p orbitals. And so when we look at it 3-dimensionally, okay, using x, y, z coordinates, they are dumbbell in shape. So you have basically 2 lobes. For a p sub x orbital, the 2 lobes lie on the x-axis. And that's why we specify that. So the lobes of the p orbitals, or a px orbital, are on the x-axis. So here we have a p sub x. So now you can kind of predict what a p sub y and p sub z would look like, right? And so the 2 lobes for a p sub y would lie on the y-axis, just like this, as shown here. For the p sub z, you will have 2 lobes that are oriented in a vertical fashion on the z-axis. So that's the difference between the px, py, and the pz orbitals. And these orbitals are, of course, different. They can each hold a maximum of 2 electrons, and the only difference is that they're oriented differently in space. And the orientation of the orbitals are represented by the m sub L quantum number, which is the magnetic quantum number. So if you were to calculate or determine the m sub L based on the L value, there are only 3 values for m sub L: -1, 0, and +1. Because remember, m sub L is dependent upon the value of L, right? So if L equals 1, then m sub L must be from -L to +L, including 0. So in this case, -1, 0, and +1. And because we have 3 different values for m sub L, that indicates 3 different orbitals. And that's why we have these 3 different orientations of the p orbitals. We have px, py, and pz, a total of 3. So now the third type of orbitals are called the d orbitals. And the d orbitals are the orbitals in the d sublevel. And the value of L is 2. So in this case, if L equals 2, then the values of M sub L would be from negative L to positive L, including 0. And so in that case, it's negative 2, negative 1, 0, positive 1, and positive 2. And so we have 5 different orientations of the d orbitals. And that's why we have the dxz, dyz, dxy, dx squared minus y squared, and dz squared. So what do these subscripts tell us? Like, for example, the xz, the yz, xy, x squared minus y squared, and z squared. Well, again, remember that the orbitals are basically mathematical representation of where the electrons can be found, right? It's a statistical probability distribution map. And so what do these subscript mean, and what do these orbitals look like? Well, the d orbitals basically look like 4-leaf clover shape, okay? And except for one of them, and that's the dz squared. We'll take a look. So looking at it three-dimensionally, right, using x, y, and z coordinates, this is what a d sub xz look like. So the lobes, the 4 lobes, lie on the xz plane. So remember that this is the dxz, and so the xz plane is basically this right here. So if you draw a square around this x, y, and z coordinate, that's your xz plane. It's basically like if you're looking at a board, or if you're looking at the whiteboard itself, and you put a piece of paper on the whiteboard, that's the xz plane. It's basically parallel to the whiteboard, okay? So that's the dxz, the lobes of the orbitals lie on the xz plane. What about the dx or dyz orbitals? The dyz orbital basically shows you that the lobes lie on the yz plane. So the subscript basically indicates what kind of plane it is, right? So it's the yz plane. So now if you have that white piece of paper on the whiteboard, you switch its position so that now it's perpendicular. It's perpendicular to the whiteboard, right? So that's basically your yz. So the lobes lie on the yz plane. What about the dxy? So the d sub xy orbital, the lobes are on the xy plane. So now, same white piece of paper. That white sheet of paper, you flip it so that now it's parallel to the ground, right? To the floor. It's parallel to the floor. That's basically your xy plane. So if you're looking at this xyz coordinate, it's parallel to the floor. And so those lobes are oriented in the same plane as the floor, basically. All right, and the fourth one here is the x squared minus y squared. And the lobes lie on both x and y axes. Okay, so you have the lobes on the x-axis and the lobes on the y-axis. So that's basically your dx squared minus y squared. And the last one here is probably the most different, most distinct among the d orbitals. This is the dz squared. So it's basically 2 lobes that lie on the z-axis, and then you have a ring around the center. Okay, so it basically looks like double pacifier. Okay, so that's what a dz squared orbital looks like. And make sure that you remember these orbital shapes, the s, the p, and the d orbitals. So for the f orbitals, you don't have to exactly remember what an f orbital looks like. You just have to remember the first 3, s, p, and d. So let's look at the basics regarding the f orbitals. So if you remember, the f orbitals are in the f sublevel, and the value of L for an f sublevel is 3. So we have L equals 3. So the m sub L, the magnetic quantum number, would have values from negative L to positive L, including 0. And so that's negative 3, negative 2, negative 1, 0, positive 1, 2, and 3. So a total of 7. So there are 7 values, numerical values for the m sub L quantum number. And so that tells us that there are 7 different f orbitals. So we have 7 f orbitals in the f sublevel, and that each orbital in the f sublevel can contain a maximum of 2 electrons. So that's why an f sublevel can hold a maximum of 14 electrons. So that's all you need to remember regarding the f orbitals. And so this part right here summarizes the different types of sublevels and the number of orbitals that are inside those sublevels. So let's go over them again. An s sublevel contains 1 orbital. A p sublevel contains 3 orbitals. D contains 5. F contains 7 orbitals. And in the s sublevel, you have s orbitals. In the p sublevel, you have p orbitals. D sublevel contains d orbitals. And f sublevel contains f orbitals. Make sure you know how to determine the maximum number of electrons possible in each orbital or in each sublevel. And so for an s sublevel, the maximum number of electrons would be 2. For a p sublevel, the maximum number of electrons would be 6. For d sublevel, a total of 10. And an f sublevel contains a maximum of 14. And so how did we determine the maximum number of electrons? Well, it will depend on the number of orbitals in that specific sublevel. You would just multiply by 2, because remember that the maximum number of electrons any orbital can hold is 2. So 2 times 1 is 2, 2 times 3 is 6, 2 times 5 is 10, 2 times 7 is 14. So that's how you can determine the maximum number of electrons per sublevel.